Okay, all right. Very quick reminder. So I had meeting with almost every one of you last week. So hopefully you're okay with this Thursday here to just demonstrate a tool. I think for that one, I don't have any big concern for any team. So no big concern, no big. Maybe some slight concern, maybe for the second deadline. Okay. So now I will urge, for those of you who have not started with the development for your compiler, notice that next Thursday will be the third milestone, where you have to give me a working compiler for all the basic features, right? Basically assignments, variable declaration, if statements, and some sort of contracts. Okay, that's what I need to see. I talk to every one of you. Yeah, precondition, postcondition, assertion, etc. Okay. Anyway. Okay, that's about it. And your quiz number 2 and 3, I got the paper. I'll give them back to you after the class. And for your quiz number 4, it will be next Wednesday, but I'll try to give you some exercises, either in class or beforehand. So hopefully get you prepared. The average was pretty high for quiz number 2 and 3, which is good. I'm glad everybody did well. And then, yeah, keep the good work.
We're learning.
You're learning. I like to hear that. Yes, you're learning. I'm learning too. I'm learning too. Good. All right. So now I would like to, about 1.5 lecture is left for parsing. Okay. We have to, today, we're going to finish some tricky work just about how you can calculate the tables actually for your bottom-up parser. We're going to do part of it. And then hopefully for the first half of Wednesday, we can finish everything about parsing. And then for the remaining of the semester, about 3.5 weeks, we can do more optimization and code generation, which is also what you're doing for the project anyway. Okay. Okay, let's talk about it. I remember, was it Ashton? Maybe you asked me that question about what's the general performance for LR1 versus LR1, basically top-down parsing versus bottom-up parsing. The answer would be they are equivalent in terms of their performance. Okay, I'll just mention very quickly, right? When you actually study later for the whole course, you may, in order to answer this question intuitively, you don't need to prove it formally. In order to answer that, think about what's the parsing process you have. Okay, I'll mention quickly, and then we can move on to bottom-up parsing. For LL1, we know that that's basically, we talk about specifically about top-down parsing, and also no backtrack. Okay, I'm just going to argue intuitively, okay, informally. The way you actually do the parsing is assuming that we got success, right, for the string, and then you start with the start variable. So this is the start variable that you start with, and then eventually, let's say there's no backtrack, so you will never have to waste your efforts of finding the match. So that means eventually you can actually do things like this, and then once this is matched, you can also try to do this and then try to do that. And the way the order in which you're trying to complete a matching, they correspond to leftmost derivation. Okay, that's what we said, right? When we talk about top-down parsing. So the performance at runtime is going to be basically is going to be proportionate to the efforts to perform leftmost derivation. Okay, let me just say this for now. Okay, intuitively. Okay, what about the one for right LR1 parsing? It's going to be a similar argument over here. Okay, LR1 parsing over here. So now we're talking about basically bottom-up parsing. Okay, of course there's no backtrack that we have to worry about. And last time what we did was we assumed that you actually got actions table, also you got goto table. We'll talk about exactly how you can fill in these two tables yourself manually. Of course, if you got a parser generator like Antler, they will generate something like that for you. Okay, if they can generate bottom-up parser. And then the way it works is kind of like a reverse, right? Remember when I try to explain them intuitively, if this is the input sequence you have, and then you're going to gradually to say this word and this word, they match this particular variable A. So you will do the reduction. And then you're trying to do bottom up, so eventually you can actually build a tree like that, eventually, right? And we said the way you do it is like a reverse order of rightmost derivation. Okay, so the way to think about the performance for these two, they are basically the same. It's like as if you're trying to do derivation yourself. So the Toronto performance wouldn't be that huge. It's just proportionate to the length of your symbols, basically. Okay, that will be my response to it. But we don't really prove it formally for this course, of course. Okay, okay, that's just some intuition for the two parsing mechanism. So now let's go back to bottom-up parsing. Okay, and what we need to talk about today will be a little bit dry, but we have to go over them, right? Because they're part of the theory. So hopefully we can get through it, and so we can start other topics as well. Okay, so this is the algorithm that we traced last time, okay? So just to mention that quickly. So if you're asked to trace somehow for some simple input, maybe in the exam, you will be given an algorithm. As I said, you don't need to memorize it, okay? It's not a problem. Okay, so now what I will go to is for LR1 item. So today we're going to see how we can calculate the different states for your bottom-up parser, the LR1 parser. That's what we're going to see today. Okay. We got action and go to tables, and then they are actually for us to find handles and reductions, right? We talked about what handles are last time. And then I forgot to do animation, but anyway. So this particular format over here, we talked about last time briefly. So you can, let me just put it on the iPad here. Let me explain that quickly. Okay, so let me put it down here before I switch to iPad. Gamma, then A. So there are several components for how you can represent the states of your parser. You can think about this is so-called an LR1 item, okay, for your bottom-up parser over here. And then you can think about this guy here, the pink one. So this part here, without the bullet points, this is a production rule. The one that we're currently trying to match, production rule. And then there is a dot for the bullet. Okay? This is actually important because later on, for you to really figure out what's the current state for your compiler or for your parser, you have to know where to put the bullet points. So the bullet point here, you can think about this, the way textbook puts it is by saying that's the top of your stack. The top of stack of your parser. Okay, and then we also mentioned briefly last time, whatever you put is a second argument here for the item. So this is a look ahead symbol. Okay, you can think about in order to really represent the states for your bottom-up parser, you have to give an item like this. You have to know how to systematically calculate it. Okay, but let's see how we can. Let's just talk about the different scenarios before we start calculating it. Okay. Okay, so now I basically explained everything here, so you can also read them through. One thing I want to mention quickly. One connection you want to draw later back to your study is this. As I mentioned, this guy over here, the bullet points. So this tells you where the top of the stack is. You can think about visually. I'm going to show you what, the example we did last time, just to draw your connection. You can think about if this is our trace stack. You can think about to the left of this particular bullet point, that tells you the contents of your stack, like a beta. And then gamma is yet to be matched. They're not matched just yet. That's why it's not on the stack. But eventually, if you can also match gamma over here, that means you can move your bullet points from here up into here. That means you have matched beta and also gamma. Right? And then you're going to see what the lookup head symbol is. If lookup head symbol is A, and also if the current word is also A. So that means these two match, and then you're done for that particular reduction. Okay? That's basically the procedure. And what I want to draw your attention to was, remember we did tracing like this last time, right? You can think about every time when we are trying to match certain, well, I'm not going to retrace it. You can think about every time we try to push onto the stack, we got some symbol here and its corresponding states. And also some symbol here and some corresponding states. You can think about up to now over here, we have already matched basically opening and closing parentheses. You can think about these are the two things we have matched so far. So you can think about the bullet points is right after the closing parentheses. Okay? You can think about the bullet point just a way to write in textual formats to tell you where the parser progress is. Okay? We're going to see many ways, some systematic way to manipulate this today. Okay? Any questions for now? Okay, good. Today, if I go too fast, try to slow me down if you wish. Otherwise, you have to do a little bit exercise. I'll assign some exercise to you at the end. Okay, so now we'll talk about LR1 item. So what we just spoke about was the formats for the LR1 item. Production rule, placeholder, bullet points, and also some look-ahead symbol. Let's see what can be given a particular production rule, where can a placeholder be? So there are three categories. Let's just go over them very quickly. We may have seen this last time. Let's see that very quickly again. And then we'll see how we can calculate them. Then you can have a better understanding. So they also have special name depending on where the bullet point is. When the bullet point is actually right in the beginning over here, which means we know that eventually we want to reduce to A, eventually. But now at the moment, we haven't matched anything yet. It's just possible we may have a match. That's why it's called possibility. Okay? And then, okay, so now again, you can see we can now, so currently on the stack, we just don't have anything regarding this particular match. We haven't matched anything. Okay? And then also recognizing beta will be the next step, and then followed by gamma. Okay, that's the first item called possibility. Okay? And the second one, in that case, can you imagine how the second one is going to be a little bit different? Well, we're still talking about the same production rule. We're still talk about the same look-ahead symbol. What really changed will be the bullet point. Okay? The next one will be, let's say we actually match beta. In that case, we have to match gamma the next. So it's called partial completion over here. So you can see the same production rule. We still got A produces beta gamma. But now you can see the bullet points over here. So that means the parser actually matches beta already. And then we just yet to match gamma. Okay? After that has been done, with the look-ahead symbol, we can decide whether it will be successful or failure. Partial completion. Okay? Finally, not surprisingly, over here, we have the bullet point here saying that up to now, we have already done matching beta and gamma. So now all we need to do is to say we may reduce to A. We may do that as long as the current word matches the look-ahead symbol A. Okay? All right, so that's about the completion. And of course, things just textual. You can also read it. Guys, any question about what we talked about so far? So far, we just talked about the structure for each LR item, right? Yes? Yeah, the question was really about ambiguity. I would say at this point over here, we don't really try to discover ambiguity at the item level. Well, here goes the roadmap. Okay, let me tell you. So the question Abdul just asked was about how can we discover ambiguity. Okay, so let me just tell you a little bit about the roadmap. Okay, so today we basically talk about LR1 items. Here we just talk about the possible states of your parser. And then towards the end of today, we also talk about something called Canonical Collection. Okay, I'll introduce the term in just a moment. It's called CC. Okay, it's basically, think about there are like a subsets of LR1 item. And after today, you'll realize the way we try to move from LR1 items into subsets of LR1 items is very similar to how we go from NFA to DFA. Remember, we did a subset construction in NFA to DFA, right? You can think about this is more like an NFA, and this is more like a DFA analogy, okay, conceptually. But we'll see exactly. And then, what you were just asking, right? Let's say if somehow we can figure out all the possible subsets of the L1 item that's reachable from the initial configuration, right? Once we can figure that out, we need to follow a particular procedure to fill in the actions and also goto table. And it is this particular procedure that we're going to discover ambiguity, okay? If you find any ambiguities, you're going to report errors over here, because if you can really generate a two table successfully, that means there's no ambiguity. If there's any one, you have to report. Specifically, maybe you have heard about ambiguity like shift reduce conflict. I'm not sure if you've heard of it before. One is called shift reduce. Another one is called reduce reduce. So this is something we will talk about to finish up the parsing topic on Wednesday. Okay, that's what we will do next time. But hopefully that can address your question, right? So we're not going to cover about ambiguity just today, but it will be down the road. Today we are still paving the road for that. Okay. Good. All right, let's go back here. And then, okay, any question about the notation here? We're going to rely heavily on this notation. Coco. Oh, so here, A, okay, the A, beta, gamma here, there's just general form. It can be, let's say, it can be factor, it can be expression. It's like a placeholder. The small, you mean the A here? Sorry. Oh, lowercase a. Oh, the A here, just any terminal symbol. You can think about A will have to do with the follow set that you guys know how to calculate previously. We'll see that. Yes. You can think about, it doesn't have to be A. A is just a placeholder, any terminal symbol, but only a single one. Okay, good. A has to be a terminal. For example, one example A would be EOF, end of file. Well, it could be character A, it could be character B, or it could be opening parenthesis. It's more or less like a follow set. You will see how we use a follow set. The A here. But it's a single symbol, right? So every time you put an item over here, it's going to be a single terminal. You can think about the terminal here is part of the follow set for A. Okay, yeah. But we don't put a set here. You just put a single symbol here, okay? Okay, so now let's see, to start with, let's see, we want to know how we can, given a particular grammar, okay? Given a particular grammar, how we can calculate all the possible or the legal items for LR1, okay? That they are not necessarily reachable stages yet, but at least we should know how to calculate them, okay? The principle is actually quite easy, but I'm just going to go over with you, okay? Let's say this is our grammar over here, and there will be something to notice, okay? You can see the start symbol is go, and also we got a list, we got pair, only 3 variables over here, right? And of course, if you want to calculate a follow set for list and pair, that should be also quite easy, okay? Now, my hints to you would be, now if you want to answer things about LR1 items or canonical collection, you have to know how to calculate follow set, okay? Either you have to calculate it, or I might just give that to you in the question, depends. So now, let's say this. How do I represent the initial states for this particular grammar? So now, before I just talk about like A, beta, gamma. So now we got concrete symbols over here, right? So now, anybody want to try? Initial states. What should be the initial state for my parser? Which means I go down list. Yes. Let's take a look and make sure everybody agrees. Basically, initial state, think about this is going to be the initial states for this particular parser. You want to do it in the bottom-up parsing fashion. I want to basically, eventually, I want to reduce from list into go, because go is a start symbol. In the beginning, I haven't matched anything. I'm expecting to match list, so that's why I bullet points here. And then the follow symbol for go will just be EOF. That means nothing else to match, right? That's one's easy. Okay, similarly, can anybody tell me if it was a success, what should be the desired final states? Go list. Follow for go is always EOF, right? It has a start symbol, right? Okay, hopefully it wouldn't be surprising to you, just like that. So now, if you look at these two, initial state versus desired final states, they look pretty much, well, maybe some of you find them look the same, no? Right? But they are different. They're very different. Notice the position for the bullet point. You can see in the first one, bullet point tells you exactly where the parser is. For the first one, parser has not matched anything yet. It's about to. But for the second one, it has matched list already. So now, as long as there's no more input, like a current word to match, let's say, for example, if currently the word is actually A, A is not EOF. That means you have not succeeded, right? But now if you're reaching the end of the input, that means the word is EOF, which is matching the look-ahead symbol, then you're done, right? Guys, do you follow what I'm trying to say here? Okay. Yeah, if you found too lost, you may want to catch up, right? Okay. Okay, we got initial state, we got desired final state. So now the problem is, how can we figure out from initial to final all the intermediate states? That's the question, right? We're going to do something today to show you a direction. You can use something very similar to subset construction. Can anybody recall, in the subset construction, let me draw some analogy to you. We're going to see that in just a moment, very soon. Okay, let's say this, right? Oh, actually, subset construction we did can apply to epsilon and FA, right? For example, good. So now let's say S1, okay? Epsilon here, and then S2, and then also S3. Let's say, very dumb, epsilon and FA. So now, question for you. When I try to fill in the table of the corresponding DFA, what would be the initial state to put? S1, S2, epsilon closure, right? Okay, good, very good. So that means you're going to say epsilon closure of S1. In this case, it will be S1 and S2, right? So in the corresponding DFA, every state corresponds to a set of states in the corresponding NFA. You will do something very similar today. But rather than using epsilon closure, we'll learn about another kind of closure. And the closure has to do with manipulating the dot symbol, okay? That's something we're going to see today. I just want to draw some analogy to you. You will find the process very, very similar. Very, very similar, okay? Okay, so now intermediate states and, okay, so this will be one possible question for you. I can tell you that once you see the answer and see the process, this one is considered as easy, okay? Derive all the LR1 items for the above grammar, okay? There will be a certain principle I will show to you at the end, okay? But now, how can we know about all the LR1 items? In some way, you know what? Interestingly, to think about the answer, iterative will be easier this time. Okay, let me give you a little bit hints, and then I'll show you the answer, and then we'll do a little bit together. Okay, think about let's say this. Let's say for this line number 1, rule number 1 over here, the bullet points can either be before the list or after the list, right? And in this case, go symbol can only be followed by EOF because there's a star symbol. Okay. Similarly, let's say for rule number 2, in this case, how many positions can there be for rule number 2 for bullet point? 3. Good. Either before the list, between the list and pair, or after the pair, right? And also depends on how many follows, how large the follow set is for list. You may have to put the look-ahead symbol differently, right? Because there's only one single look-ahead symbol you will put. Okay. Okay, that's a very quick sketch. Now, in order to develop the answer, let me help you a little bit. Okay. First of all, double check for yourself, like these are correct. Okay, I wouldn't waste your time in the class. Okay, double check yourself. When you calculate the follow set for list and calculate the follow set for pair, that's what you will get. Okay, good. Let's assume that's true. And then I'll give you the general formula. It's a set comprehension expression. I'll show you first. You can take a look. I'll give you some intuition, and then we'll do some examples together. Basically, you have to consider for every production 1, 2, 3, 4, 5, right? You can think about we got 1, 2, 3, 4, 5, 5 productions in total. For every one of them, you have to say, given the follow set for that particular left-hand side symbol, okay? For example, if you're considering rule number 4, you should consider the follow set for pair, okay, for example. And then the corresponding LR1 items will be, okay, let me show you the formula first, and then we'll see how to calculate it, okay? It might look a little bit scary, but it's not that. First of all, you can see, again, I'm trying to talk about this particular, oh, sorry, there was a little bit typo here. It should be A produces beta gamma. Okay, that's what I meant to say, okay? So now over here, I can say either the bullet point can be before the beta, or the bullet point can be between beta and gamma, where the bullet point can be after the gamma. So we got, see, can you see some kind of a concept about cross product over here? Okay, the left-hand side for the cross product is about the positions of the bullet points, which can be basically either before, intermediate, or after, depending on how many symbols you have on the right-hand side. Okay, when I say symbols, it can be variable as well. And then the right-hand side for the cross products depends on the follow set for the A. If the follow set of A is simply of size 5, that means you're going to multiply that by 5. It's kind of the idea of a cross product. Okay, let's see one example. Okay, let's say for this particular example, let's say pair produces parenthesis, pair, parenthesis. Okay, what will be the corresponding LR1 items? How many, first of all? I heard 12. How did you figure?
Follow, there's 3, and there's 3 symbols, which means there's 4 positions and 4 actions.
Very good. Okay, well, Ash can just set. Let me just repeat slowly here. And then we'll see exactly how you generate, right? I wouldn't expect you to be this quick. Even myself, I'm maybe slow on this. First of all, you will look at the right-hand side. The size of the right-hand side is simply just 3. That means the bullet point can either be before the left parenthesis, can be here, 2, can be here, or it can be after this, so 4, right? And also you consider the follow set for pair, which I gave to you. Follow set for pair is EOF, right? EOF or left or right. So now if you try to multiply these two sets together, you get basically 12. Let's see. So now it can either be before, okay, we consider this particular production rule. It can be before, it can be in the middle, it can be after the pair, it can be after the parentheses, right? We got 4 here. This is only partially what the LR1 item will consist of. And then, what about the look ahead symbol you can put? It depends on the follow set. And the follow set for pair is simply this, what I gave to you, is size 3. And now, how can you combine them together? That's the question. Okay? How can you combine these, all these together? Cartesian product, that's pretty good. Yes, exactly. Okay, so now all the possible ones, okay? Before I show you the answer, okay? Before I show it to you. Okay? Okay, before I show it to you, let me just show you one particular part of the calculation in case you're not really following. Okay? So now let's say we talk about this particular rule over here, just this particular one. And let's say for this one here, the item, okay, the LR1 item. Okay? Start with the square brackets, and then the right-hand side is simply this. And then one possibility would be right before. We haven't matched anything. It's to be matched. Pair and this. And then we know that the follow set for this pair is basically just EOF. That's one possibility. Or with the same over here, the look ahead symbol can be different. And then can be opening parenthesis, or it could be the same over here, and then pair, closing parenthesis. So these are the 3. Everybody okay with this? Okay, hopefully you're fine. Who, are you convinced?
Just one question. We do LR1 items for every rule. We do the LR1 item calculation for every rule. So rule number 1, rule number 2.
Exactly. Yeah. If the task was to come up with everything. Okay. Then of course you can see it's a simple process, just systematic, just a bit tedious. Okay. Yeah, it could be, but as you will see, yes, you will see that the set of LR1 items over there are all the possible states you might actually reach for your parser. However, only only all the valid states, but only certain states are reachable from the initial configuration, as we'll see. Okay, so we'll see that. Okay, okay guys, hopefully it will be easy for you to imagine. So now you have to really try to say, for example, this bullet point can be here, and can be here, right? Okay, so you can figure out the rest. Okay, for that one it's easy, so I don't want to waste too much of your time. So now this is one possibility, right? With the other 3 follows the all the three look ahead symbols. You can be here, can be here, can be here. Okay, so these are all the 12 LR1 items. Okay, everybody okay so far? Okay. And now, how many in general? Can you have a formula for this? Formula. So let's say this. I may not ask you to actually write out everything, right? I might simply ask you, given production rule, pair produces parentheses, pair parentheses. And also given the follow set for pair is simply EOF, opening parentheses and closing parentheses. In this particular case, the size of the relevant L1 items is 12. In principle, what would that be?
That's just one rule. That's just for one rule.
Just for one row. Given a particular row, of course, if you want to come up with all the LR1 items for a particular grammar, you have to add up all the rules. Okay, you're saying somehow you have to see what's the length of beta and gamma, see how many of them are. Should you plus one? How many bullet points? Plus one, right? Because it could be beginning and the end. And then also times the size of the follow set for that variable, right? Good. Okay. So this is not really a hard formula, so we simply say, in this case, if you look at this particular right-hand side, you got 1, you got 2, you got 3. So the size is 3. In that case, you know the bullet point can be 1, 2, 3, and also 4. So that's why it's the size of the right-hand side plus 1. And then also multiply by the size of the follow set. Okay? Questions?
We were just talking about L1 follow A.
Huh?
How would you figure out the upper bound for follow A?
Upper bound for follow, oh no, I'm just saying this one depends on the size of the follow A. So it depends on that.
Nobody's trying to upper bound.
Like, yeah, but like just follow A.
Follow A really depends on the grammar itself, right?
But you were saying
So
that.
upper bound size of the alphabet.
Sure?
Yeah,
Yeah, true. But I think this one, but sometimes your follow set might just be of size 1. So I think if you just say upper bounded by the size of the alphabet, may not be accurate, right?
No, but if you're looking for worst case memory usage, then it's probably-
That's true, true.
It's probably achievable
Mhm.
by some grammar, not by all grammar.
Yeah, so I think, yeah, you can always try that. Depends on the alphabet set. Yeah, I think this is more precise, right? Yeah, good. Okay, so now this will be the final answer, okay? Okay, don't worry, if I really ever ask you to calculate this, as you can see, the calculation itself is not difficult, right? It's trivial, true. Huh? It's quite a bit. I would say the most extent, if I ever want to ask you for your understanding about this, I wouldn't give you a grammar and say, come up with all the LR1 items. It's not that interesting. What I might do is maybe I would say for the particular, for example, it can be as easy as I would say, come up with all the LR1 items for, let's say, the go symbol, this particular production rule. So in order to do that, you have to know how to put a position for the bullet points and also what will be the follow set for the goal, right? Okay, that would be what you should do. Okay, guys, questions for this? Okay, so again, we're just trying to see what are all the possible potential states for your parser, but only certain subsets are actually reachable, as we will see. Okay, we haven't reached the second stage just yet, but we will when we calculate the closure. Okay, so now I'll just give you one exercise over here. So now over here you have the grammar over here. So this is some grammar that we examined previously. So this is actually the right recursive grammar that we talk about. Okay, and then also you got some epsilon production. Okay, so what you want to think about, you don't really have to. Okay, the question itself, I say derive all the LR1 items. I would say just choose one variable and then try to see what the LR1 items is. Okay. Can you see? Okay, how about this? Just see one of them. What will be the initial state, first of all? Go dot expression. Okay, good. What will be the desired final states? Go expression bullet points. Okay, that one's easy. Okay, that can be some easy question to answer, right? And now, let me just tell me the size. Okay. And of course, to be fair, I have to give to you the follow set, right? So you know, you don't have to calculate yourself. Okay, let me make the question as easy as this. Okay, just ask you the cardinality of the size. Okay, that's the whole set over here. Okay, and let's say this. Tell me what's the cardinality of the LR1 items of. How about we just choose? Let's say. How about this? Rule number 2. How many? Well, first of all, how many positions can you get for the dot? Can be 1, can be 2, can be 3, can be 4, right? Okay, 4 of them. Multiply by, what's the size for the expression prime? Either EOF or parenthesis, right? Okay, so that will be 2. So there should be 8 of them. Okay, if I just ask you that question, that should be easy to answer, right? Okay, good. And you can try others as well. And one thing to note, in this particular grammar, which is also very common, you might have epsilon production, in which case you don't have to worry about them. You wouldn't put the dot before and dot after. Doesn't make sense, right? Epsilon would just be matched right away. So in some way, the epsilon has been taken into consideration in the follow set. So you don't have to worry about epsilon production. You will see that statement in the slides. Okay. Okay, so that's about it. Okay, so we finished the first stage for the lecture, well, for this topic here, which is just about to figure out all the LR1 items. Okay. Any questions? Okay, good. So now the second stage is really to figure out how to calculate closure. Okay. So there are 3 routines we had to see. Okay, I'll try to go over them quickly. One is about closure. The other one is about goto, which is mainly to calculate transition. And the third one is about basically the overall algorithm, which is very similar to the subset construction. Okay? Again, we go over them by using the example to see conceptually how they work. And if I really want you to calculate that, I'll give you algorithm. Okay? You don't need to memorize, but at least you should understand them conceptually. Okay? So now this slide here is very important because now we are switching from stage number 1 to stage number 2. In stage number 1, we talk about LR1 items, which is pretty straightforward, right? You just have to think about the Cartesian products between the follow set and the position of the bullet points. And now what we need to think about is something called canonical collection. Okay? And let me just go over a little bit slides with you. There might be some background you might need me to explain. Okay, we'll see. Okay, remember overall we got 33. Okay, and also we got initial states, right? You might be thinking that potentially we might got 33 possible states. Not quite. 2 to the 33 is the correct answer. 2 to the 33. And? Huh? No, 2 to the 33. Basically, I'll explain that in just a moment, right? Basically, think about all the 33. Thinking this way. Let me just give you a little bit of intuition here. Think about in this way here. Okay, here. We got 33 LR1 items over here. You can think it's the whole set, right? And now think about these are the possible states in the NFA. Okay, try to draw some analogy. Every corresponding DFA that we're going to construct is going to be a set of this set. How many subsets do you have? 2 to the 33. Because for every of the 33 items here, you can choose either to include it or not to include it. That's why it's 2 to the 33. So when was the last time you tried to deal with power set?
That's approximately 10 billion. That's approximately.
No, that's not my question. My question was, when was the last time you deal with power set? Power set. Yes, I mentioned that in the slides. But what about was it in your 1090, 2090? 2030. Really? They talk about power set in 2030? Oh, yeah, 2030. Oh, that's what you meant. Okay. I thought you talked about OOP, that course. Okay. Yeah, you're right. You're right. Yeah. Anyway. Analysis 3? Good. Good. Good for you. Good for you. Yes, I asked. And you answer me. That's good. How nice. Okay, so now over here, so we got initial states, we got LR1 items. Good, that's what we know about. So now let's talk about canonical collection. Okay, definition here basically says the following. Okay, let's be very careful when we define it. So when we calculate, you wouldn't get confused. I'm going to use CC over here for canonical collection. It's going to be a set of subsets, basically. You can think about we're going to have CC0, CC1, CC2, all the way to CCN, depending on how many you have. Okay? How many you have over here, how large n is, depends on how many reachable subsets there are when you do the subset construction. Remember the lazy evaluation we did? It depends on that. Okay? And CC0 over here, if I just refer very quickly back to a diagram I drew. Okay? CC0 over here basically just correspond to this guy here. That's a starting point for the table. Okay? You're going to build it up, basically. Okay? And of course, at the end of today, we're not going to build a whole table. It's going to take maybe 10 lectures to do that. Right? Well, what I will show you is maybe just filling a particular cell over there to see the idea. And then we'll go from there later. Okay? Good? So guys, for now, get it clear that every member in the CC, canonical collection, is a subset of the LR1 item. That's the first of all, it's a set. Okay? And then it's a set of items. And now you shouldn't be too surprised. We say that CC is actually a subset of the power set. Okay? I would say think about this particular line over here. Okay? For now, I assume everybody is okay with power set. Okay? If everybody is really, really struggling, maybe next time I can mention that briefly about power set. For now, I just assume to save time. Unless somebody insists I should talk about power set quickly. Everybody's okay? Don't be shy. Good. Nobody's shy. Good. Okay, so now, what will be the size for CC? Upper bound. 2 to the power of? Exactly. Good. Okay, it's a very quick check, right? Because you know it's a power set relation, so that's the cardinality, right? So in theory, when you try to calculate a CC from a particular grammar, you may have to go up to 2 to the power of this particular LR1 items iteration. You may have to. However, in practice, you may not have to, depending on your grammar. I'll say for this course, you don't have to worry. Any question I give to you, you're not going to calculate the whole thing. Usually, you will just have a tool to do it. Okay? If I ever ask you a question related to this, I just want to make sure you can do a tiny step over there. Okay? That's all I will ask. Okay, and then to really model a LR1 parser, okay, so now we're going to get to the subset construction soon. What we need to have is we're going to use techniques similar to how we did it from the NFA to DFA. So we got subset construction and closure. No epsilon here, just closure. Okay, and closure might be the tricky part that we have to go through first. And after that, we'll just see how we can build the transition. Okay, let's see. Analogies quickly, and then you have basically LR1 items are like the states for the NFA, and also canonical collection is like a subset, the subset states of the DFA. Okay, that's how you can draw a connection. Okay, any question about this page? So this page is to really make sure you wouldn't, later on when you study the slide, you wouldn't be confused why we are suddenly talking about CC as opposed to LR1 item. That's the reason. Okay. Previously, we talked about LR1 items, so now we talk about the reachable subsets from the initial configuration. Okay, the first algorithm to go through is something called closure. Okay, good, closure. As usual, let me just go through line by line very quickly, and then there were certain parts I want to explain more quickly, and then we can just try to do one example. Okay. For the closure, you're going to get some grammar. Okay, context-free grammar, and then you're going to get a set of LR1 items. Okay, any set, basically. Given a set, I want to know what's its closure. Okay, and the set can be a singleton set. That's fine. Okay, just a set. And the output is just going to be another set, being its closure. Okay? And then I'm just using this particular, I'm just using this particular variable last s to make sure as soon as I have last s equal to s, that means I finish. I cannot add anything new to the set. I'm done, basically. Okay? To make sure I got fixed point calculation. Okay, just like over here. Okay, so now you're gonna see some very, very scary definition over here, but we're gonna go through it. Okay? This one is saying, line number 8, you're trying to identify in your existing item in S. You want to find out for every one of them if they are of a particular shape. Okay? The particular shape goes like this. The bullet point is here. Before that, you got something, dot, dot, dot. Okay? How about I switch to iPad very quickly? And then when you go through the algorithm, what you will see is I got explanation for every one of them. You can read them through. Okay? But for now, I'm not going to read it through the slide. I'll just give you a little bit intuition, and then we'll do examples. That might be the best way to get you hopefully started on that. Okay, so now we are here. Okay, let me just highlight some important steps for you, and then we'll do one example together. Okay, so that's the algorithm. Not many lines. Okay, you can think about this particular for loop. We are basically trying to identify an item that's in the input S. Okay, just any item. So eventually you have to go over all the items. Okay, eventually. Okay, and then dot 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 here simply means anything, which could be epsilon if you want to. Could be. We'll see examples. And then this is the current position of your top of the stack, and let's say there is certain variable over here. Okay, and then this is the remaining part of the production row on the right-hand side. And this is a look ahead symbol. Okay, that's a very general structure. We're going to see example. Okay, and then for all such item there, we're going to see over here. We're going to see for this particular C over here, if you see this particular item, this tells you the next to match. According to what we learned so far, how do you interpret this particular item? What will be the next one to match? C? Agree? Immediately after bullet point, right? Is that what you want to say? We got another question.
The delta is any sequence of circles as well, right?
Any sequence, yes. Could be epsilon as well.
Where do we get the A from? The input is not.
Oh, A will also be, remember the input is simply going to be a set of LR1 items. They should, each one of them include a look ahead symbol. Good, it's good that you ask. Good. The A here, again, when we talk about algorithm, these are just placeholders, right? Good.
Basically, you're just going through every rule in the set.
Yes, however, you know what, interestingly, you will find that only certain items in your initial set will trigger some extra items, only certain ones. So the way I'm going to trace the example, I'm going to cheat a little bit because I know which sequence you should follow. Of course, when you do it, the actual example you have to go through by yourself, right? Just to save time. Let me admit that. Okay? Sometimes cheating is good, sometimes. Okay, the next to match is C. Very good. And now we want to say for all the possible reduction you can do from C into C, basically. So now if you have C produces gamma over here, that means gamma can reduce to C. Okay? That means we're going to basically make a new item from this particular row. You're going to make a new item from this production row. Let me talk about the look ahead symbol later. Okay, that one is a little bit trickier. But let's see this. What you will see is we're trying to expand the closure for this current iteration by this particular item, right? You can see produces gamma, right? That part is actually the one I will just talk about here. But what should we look at his symbol? That's the interesting question, okay? The way to figure out the look at his symbol is by looking at this. You can see, let me use different color here and show it to you, okay? Abstractly, let me just explain and then we'll see concrete example. you can see currently the dot is over here, which is C will be the next one to match. What can follow C? You would think that's delta, right? What if delta is epsilon? That would be A. Agree? Okay, so the important question is, I put it here. What can follow C? Okay, let's be more precise. Huh? The first of what can follow C? What you really meant to say was this. Okay, that's good. Okay, what you meant to say, you just said the wrong target, right? I think what Miska was meant to say, what can follow C in this particular context will be the first of delta A. Delta followed by A, basically. That's interesting because if delta itself is not epsilon, then A has no use. But delta can be epsilon. You will see example like that. In that case, you should say A. Okay, let me just put it down. Okay, you will see all these when we trace the algorithm. Okay, what can follow C? It could be either A if epsilon is actually in the first of delta. More precise, or it could be just first of delta. Otherwise. Yeah, think about this condition over here more carefully. I also, in the textbook, they also got some detailed explanation. But
That would actually be A in the first condition. If epsilon is in the first of delta, it should still be A union first of delta minus epsilon.
yeah, something like that. Yeah, you can update that. Good. Yeah, good. Okay, so now let's go to the next one. So now once you figured it out, okay, that's what you see. We're going to figure out for this particular set, first of delta A, you're just going to see for every symbol that's actually there, it could be a singleton set, or it could be multiple, or it could be empty set, depends. Right? In that case, every B, you're going to put it here. Okay? So that's the algorithm working in an abstract sense. But now we have to see how to calculate this. Right? That's going to be the, actually not tricky. I think you just understand this algorithm abstractly is a bit tricky. But let's see example. Okay, let me present to you the problem first. Okay. Okay, so now let's say given the same grammar over here, remember we say initial states. So now we want to calculate what's the closure of the initial states. Okay, and then I said it's actually CC0. That's basically the first member in the canonical collection. Okay, the closure of that. And what would that be? Eventually, this particular item is going to trigger 8 additional items into it in the closure. Okay, that's going to be the process. Okay, I tried to set it up in a way so it wouldn't take forever for us to trace, just to give you the idea. Okay, guys, ready? Let's do the closure. Okay, all right. But I promise, again, we definitely have to finish everything about parsing by the first half of Wednesday for sure. We're going to move on to other topics as well. Okay, but these are important, for the theory. Okay, how can we calculate that, right? Before I get, okay, let me just switch right away here. What I will do is I'm going to show you the different steps. Basically, let me just tell you the road. Just give you a little bit of look ahead to see what's going to happen when we try to calculate a closure. We're going to talk about the same. We're going to talk about the same grammar over here, and every time we're going to use a different rule to actually trigger some extra items to be generated, right? Okay. Eventually, we need 1, 2, 3, and 4. 4 steps in total. Eventually, okay. We're going to see one by one. Okay. Let's see step number 1. Okay, let me help you a little bit. Okay, you know what? Just for the very first one, let me just put the algorithm over here. So you will get just for the first one. Later on, you don't need to have the algorithm. Okay. Remember in the algorithm itself, let me enlarge that very quickly for you. Remember this particular item pattern, right? That one there, right? So now I got it exactly over here. Okay, just for your convenience. Can you tell me very quickly Because initially, the only thing we are getting is the initial states, because we're trying to calculate the closure for initial states. That's all we are given, right? Can you tell me how you can match from this concrete item into this abstract item? What is A? What is beta? What is C? What is delta? What is A?
Beta is epsilon, C is less than delta is epsilon.
Okay, yeah, that's quite obvious, right? Okay. My point is, in order for you to really calculate that, you have to see which one is which. Okay? Let me just point to you over here. You can see beta over here is simply epsilon. A over here is the goal. And then the C over here is the list. Right? So you can see the C is right after the bullet point. So that's why list is also right after the bullet point. Okay? And then what about epsilon over here? Sorry, delta is epsilon as well. Okay? A is EOF. Guys, any question for the first step, right? Abdul.
How come we started with a dot after beta and not before beta?
Which one? Oh, okay. If you remember, your Abdul's question was, why is the beta over here actually after the beta? Because it's just a general form that we want to choose from, right? Because you can see over here, according to the algorithm, we're saying that it's just going to be something. Here, I just say the beta, okay? You can also think about it dot, 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 just something, okay? And then also C and delta, etc., right? Okay? So now, what we want to do now is to calculate exactly how this, okay. In order to really figure out the corresponding items for that, we should also know, right? Because you can see over here, we should also find out all the production that can expand the list, right? You can see the list is more like the C over here, right? So now we want to find out all the production that can be produced by C. What do we have? You have either list produces this or list produces pair, okay? Okay, so far so good. And now, that's why I highlighted them. And one more thing that we should figure out, one more thing, before we can enumerate them. The first. And now, according to the algorithm, we talk about what can follow C. Basically, delta A, and calculate it first, right? What's delta A in this case, if you can tell me? Okay, let me write it out, okay, just for everybody. So now, epsilon EOF. So would you agree it's simply just EOF? Okay? So now all we got to do is to really do the following. We're going to actually produce this particular item and add them in. Okay? For the first one, let's do it from scratch, just for the very first one. How many should we generate? How many? That's the question. According to the definition, for all the production rule and for all the first symbol, right? There's only one symbol in the first set, right? But how many production rules are involved? Two and three. Okay? So now how many new items should we produce? 2. Coco, are you following? Good. Can you tell us what should be the 2 items? First one, please. Okay, I got list. Okay, so now according to the rule, the dot should be in the beginning, right? Okay, good. So now I should say list produces dot. Very good. And then EOF. Good. And also the second one would be list also produces, right? List produces pair. Dot. Pair. Thank you. Let's name this 1 and 2. So this, you can think about this is the very first iteration for closure. What that would do is actually going to generate 2 extra items. So now that means our S has been, the canonical set, the closure, has been expanded to of size 3. That doesn't necessarily mean we are done. We're going to do another iteration. Okay?
One full iteration.
Yeah, you can think about just one iteration. So for the whole thing. And then what we gotta do is go back to this particular outermost for loop to find out another production rule. That's why I said I would cheat a little bit in the lecture. I know which one to go for. Yes.
In the algorithm, the way you have it set up is that the initial for loop goes through every element in S.
Mm-hmm.
Like we've already processed like 0, right? In the following iteration, do we ever have to go back to 0? Like realistically, I don't think we would, because 0 would always give you the 1, 2 that you labeled. So you really need to only keep visiting, and while there are new ones, then only
Exactly.
visit
Mm-hmm.
new ones.
Yeah.
Remove it from S.
Hmm?
In some sense, you can remove it from S, put it somewhere else, and then add it back to like S.
Mm-hmm. Yeah. Yeah.
You don't need to revisit 0 anymore.
Yeah. You don't need to.
Visit 1 and 2.
That's true. Yeah, but I would say I would say maybe the most feasible way. Again, this might be something you will code it up in this way, but when you actually calculate by hand, you actually do it the way that's intuitive to you. Yes, absolutely. Yes. Okay, guys. Any question about the very first one? For the first one, we built from scratch, and for the later 3 steps, I'm going to go a little bit faster, just to give you point to you what you should really look for. Okay. So now when you actually, I'm going to keep the iPad's notes as clean as possible. For the later steps, you can also try to practice, okay? And you can just bear with my writing, okay? So now, after step number 1, or iteration number 1, what we will get is, basically, we got basically 0, 1, and 2. So these are the 3 items we got, right? So now the question is, which one can actually further trigger some new items, right? 1 and 2, yes, both of them. Yes, because for 1 over there, you have list, you can try. Because list also maybe has some first, has some additional first that can follow. And also you can do this one as well. But let's say we choose this one particularly, right? The order in which you do it in the exam or in the quiz doesn't matter as long as you got the final answer correct, okay? Let's say we choose 2. Yeah, let's say we choose 2. I'm pretty sure I'll do 1 at some point. Yeah, yeah. But in your answer, you can choose 1 or 2. Doesn't matter.
The order doesn't matter.
The order doesn't matter. You will eventually get to the fixed point. Eventually. Yeah. All right. So guys, let's say this guy here, right? So now it shouldn't be too strange to you. We should really figure out what's beta. Again, what's beta? Empty string. Okay, similar. Okay, beta is simply empty string. And then we got dot here, and C is pair, and also followed by pair, nothing. So delta over here is epsilon, right? Okay, good. And should I, okay. Now, what will be the first set? Miskov. Epsilon followed by EOF. EOF, right? Good. I agree with you. Any volunteer to actually tell us what should be the expansion? Any volunteer? Let's do this one as the first, last one, and then I will leave the final 2 steps for you. Okay? Okay. Okay, Miskov, how about that? You tried that the previous one already. Sure. Yeah, I'm sure you know how to do it. Okay. Okay, Miskov, please. Apparently, we are trying to use the pair, right? So that's why I highlighted 2, okay? And also, we only got 1 element in the set, so only should be 2 items. Right? Good, go ahead. Pair. Pair produces, right? Dot, yeah. Yeah, exactly. Just repeat that rule, and then followed by EOF. Look ahead, right? Second one?
Second one is pair followed by dot open parentheses.
Mm-hmm. Very good. Very good. Exactly. Let's call that 3. Let's call that 4. Right? So now we got halfway. Right? So now after that, you will see basically 0, 0, 1, 2, 3, and 4. Okay. So now let me just mention that as an exercise for you, I want you to try to complete the final 2 steps. Right? Basically, for step number 3, if I chose to expand this particular list, being the C, right? I'm going to use these 2 rules. Okay? And then for step number 4, I'm going to choose this particular one and expand pair. Okay? Eventually, you should really get 9 items in the initial configuration. Eventually, what you will get is CC0, right? What we're trying to calculate will contain from 0 until 8, 9. That's what you will get, okay? You can think about this as a primitive step for subset construction. Just calculate the closure, okay? Any questions?
So we're going to use this to build the action of the other thing.
Exactly, we're going to use that in just a moment. Yeah, you can see we're just trying to build that gradually, right?
For CC0 or?
That's only for CC0. Remember from the very initial question over here. Okay, remember we started with just this initial state, right? And we want to ask what's the closure of that. It turns out the closure of that has 9 elements, which means applying the closure procedure to here will trigger generation of 8 extra items.
Yeah, but then we have to do it for CC0.
Okay, now question is, how do you know what CC1 is? Hmm? Well, actually, what Mahu's question was very important. We're thinking this way. Let me put it this way, right? Let's draw an analogy to subset construction. Right? It's a very important question. Let's say this is the corresponding DFA. What we just did was we did CC0, right? Which is a closure of these initial states over here, right? So now, somehow, by taking some transition, we might go into CC1, for example, right? But now, what should be the transition, basically? What will be the transition in our context for parser?
Basically, what will be the initial state for CC1?
The transition will be what we would do.
The transition, no, okay, that's right. But can you say it again?
So you're asking what's the initial state when you
No, no. Initial state we are pretty clear. For initial state, it's simply CC0, which is the closure of this initial states. I meant the initial state for the corresponding DFA is simply the closure of the initial state in the NFA. How about that? Okay, good. So now, how do we figure out CC1 or potentially maybe CC2 and etc. Right? We want to build out all the reachable subset states.
we move the bullet points?
So how you want to move the bullet points? Yes. So basically, you can think about conceptually. The transition over here is going to be some shift. Just conceptually, just for now, okay? It's going to be some evolution of your parser, okay? We're going to see that, okay? All right. In order to actually find out this particular transition building routine, we want to see another procedure, which is called goto, okay? So now we are done with the closure. We want to do goto quickly, okay? Let me do that quickly. I got 5 minutes. Okay, let's see the goto. The goto is not difficult, okay? The goto over here, basically, again, I can just stay in the iPad over here. Let's think about what the goto will do. You can see the coding itself is actually not very long. Okay. So the goto procedure is going to take a set of LR1 items. For example, it could be CC0. Could be, right? And then it's going to be a symbol X, which means if the parser can recognize one symbol in the input, right? Like an X. And then what it will return is just another set of LR1 items. You can think about it this way. If you're given CC0 over here, and then you're trying to, say, shift by X, and then whatever is going to return is called a goto CC0, if that makes sense to you. Conceptually, that's what's going to happen. Of course, the source state can be CC0, can be CC1, can be CC2, and etc. Okay? Let's take a quick look how this should be computed. Let's go for the goto, and then I'll point to you the transition table. And then we'll finish the final bits on Wednesday. Okay? So now what we will do is, you can see the loop here. We're going to go over every item in the CC0, for example, the source set. And then, since our goal is to shift X, so what we will see is, we're saying the following. For every item that has this particular pattern, okay, let's take a look. Can anybody explain to me what's the intuition for this particular item, except for Ashkan? He's thinking too fast. I would love to point to you, but let's give everybody some opportunity. Mahu.
You want to move it, so that's why I want like
No, Mahu, how about this? Try to, if I simply give you this item here, I want you to explain to me what does this item mean particularly to describe the parser state. How would you describe it? That's my question.
If the item is part of the CC set,
Okay, anybody? Well, my question is, somehow I want you to explain to me, given this particular item where the dot is somewhere in the production, how would you explain the states? How do you describe the states intuitively?
X is the next transition.
So X, okay, X is the next transition. That's almost correct. You basically say, okay, I'll write it down. I'll sketch a little bit. You want to look at the definition in the slides, okay? So that means currently we are trying to reduce alpha. That's the left-hand side, right? We have already matched beta. Okay, that's what we have done so far. And then the next one to match will be x and also delta, right? Specifically x. Okay. Next to do will be x. Okay. So now we want to really say, because we know specifically x for this particular rule is really the next one. Basically, find out all the items where x is just the next symbol to shift. Basically, find them out and then do the shift. That'll be the part of the next states for the goto. Okay. So now it shouldn't be too surprising. Can you see what the difference is between the purple and the blue? Don't tell me they look the same. They look quite different.
You matched X and you look.
Yeah, exactly, right? So just for everybody to make sure they see it. Okay, good. So basically, so that means if I know that in the identify stage, I know that X is to be matched. And now in the new item, I want to make sure X is matched. Okay, that's what I will do. So now let's do just one exercise very quickly for goto. Okay, shall we? All right, guys, how about this one here? Right, I try to make the example connected. Right, previously we calculate CC0 to be the closure of the initial states for the parser. Right, so let's assume that's there. Right. Oh, by the way, later on, once you complete the exercise on the iPad, so that's the answer to check. Okay. So the question is, given this particular grammar over here, and also given this as the S, right? And also symbol over here is closing parenthesis, right? Now we want to know what's the next states. Oh, actually the goto, right? That's something we want to find out. Am I running out of time? Okay, good, no problem. Okay, how about this? I would say I'll pause over here. I will make sure I finish everything about parsing in the first half. We're gonna move on to other topics, okay? And if you want to stay to pick up your quiz paper, stay, okay?